JSON looks simple until your Python code starts failing with strange errors or nested data that is hard to read. In this video, we will go through 16 real Python JSON examples you will actually use in projects, APIs, config files, and interviews. We start with the JSON basics you use almost every day in Python, reading JSON text and producing JSON text for other systems. In real services, an incoming API payload usually arrives as a JSON string. Let's write a small payload, parse it with JSONDecodeError, and then pull out the user fields like regular Python data. Now we run the script and check that the nested account status is read correctly. Let's break down why this works. JSONDecodeError does the JSON parsing for us and gives back Python types, dictionaries, strings, numbers, booleans, lists, and none. After that, accessing user and account is just normal dictionary indexing. Now we show the important rule for production code. Use JSONDecodeError for JSON text. It understands JSON syntax, handles escaping correctly, and avoids the security risk of trying to evaluate incoming strings as Python code. For a quick variation, add another field under account, like renewal date, and print it from the parsed dictionary. This keeps the same pattern but makes you practice one more nested lookup. A CLI tool often needs to print configuration in a format another program can consume. We keep the data as a normal Python dictionary while we build it, then use JSON jumps to create the JSON string. Now we run it and look for valid JSON with double quoted keys. Let's explain the result. The Python dictionary became one JSON string, and JSON jumps handled the JSON spelling rules for us. Notice especially that Python false was written as lowercase false, which is the JSON version. Now we show the safer habit. Let JSON jumps build machine-readable JSON. Manual F strings are easy to break when values contain quotes, booleans, lists, or nested data. Try adding timeout seconds with the value 30, then run the script again. You should see it appear as a JSON number, not as a quoted string. Next, we make JSON easier to inspect while debugging, without changing the actual data. When an API response has nested objects and lists, compact JSON is correct but hard to inspect. Let's print the same response twice, first as compact JSON, then with indent and sorted keys. Now we run the script and compare the two outputs side by side. Let's break down the difference. The first print is ideal for machines because it is short. The second print is for humans, indentation shows structure, and sorted keys make repeated runs easier to compare. Now we show the practical rule. Pretty print JSON when a person needs to read it. For network calls, files at scale, or queues, compact JSON is usually better because it saves space. For practice, change indent from 2 to 4, then remove sort keys. This makes it clear which option controls spacing and which option controls key order. Now we move from JSON strings to JSON files, which is the pattern you use for configs, reports, exports, and automation scripts. Automation scripts often keep deployment settings in a JSON file instead of hard-coding every value. To keep this demo self-contained, we create config.json first, then open it and parse it with JSON load. Now we run the script and confirm the values came from the file. Let's explain the key detail. JSON load expects a file object, not a string containing a file name. It reads the file content, parses the JSON, and returns a dictionary we can use immediately. Now we show the best file handling pattern use with open. Python closes the file automatically even if parsing fails later, and encoding makes the file read predictable across machines. For a quick variation, add service name to the JSON file and print it after loading. This is the same pattern you would use for feature flags, regions, or deployment targets. A script that generates a report should save structured data, not a custom text format. We build the report as a Python dictionary, write it to report.json with JSONDump, and then read the file back so we can see exactly what was saved. Now we run the script and inspect the file content in the terminal. Let's break down what happened. JSONDump did not return a string for us to print. Instead, it serialized the dictionary and wrote the JSON straight into the open file. Now we show the naming rule that prevents many small bugs. Use dump when writing to a file, and dumps when you need a string. The S in dumps is a useful reminder that the result is a string. For practice, add duration seconds to the report dictionary and save the file again. Then read it back and confirm the new field is stored as JSON. In this section, we handle the point where JSON enters the program. The goal is to fail clearly when the text is broken and to validate the data before business logic uses it. Vendor feeds are not always clean, and one bad comma should not crash an import job with a giant tray peg. Let's write the parser at the input boundary, then catch JSON decode error and print the message line and column. Now we run the script and see a controlled error instead of an uncaught exception. Let's break down why this output is useful. The JSON is syntactically invalid because there is a trailing comma before the closing brace. The exception object gives us a human-readable message and the exact position, so the bad feed can be fixed quickly. The best practice here is to catch JSON decode error, where outside data enters your program. Use that moment to report enough context for the vendor, user, or log reader to fix the actual source data. A sign-up payload can be valid JSON and still be useless for the application. Let's parse two payloads and run a small validation function that checks for email and password. Now we run the script and compare the incomplete input with the valid one. Let's explain the result. The first payload parses successfully, but the validation step finds that password is missing. The second payload has both required fields, so the script prints a success message. The best practice is to keep parsing and validation separate. First, turn the JSON text into Python data, then check the fields your feature actually requires before using the data. Now we move from safety checks into everyday processing. These examples show how JSON arrays, nested objects, and limited JSON types become practical Python code. A reporting script usually gets many records at once, so JSON arrays are common in real data work. Let's parse an array of orders, keep only paid orders with numeric totals, and then sum the revenue. Now we run it and check the count and total. Let's unpack what happened. The outer JSON array became a Python list, and every object inside became a dictionary. Because the data came from outside the program, the filter also checks that each item is a dictionary and that total is numeric. The best practice is to treat external arrays as untrusted. Before calculating totals, check that each item has the shape your code expects, especially in scripts that process vendor or API data. Customer profiles often have optional nested data, and direct indexing can crash when that section is absent. Let's write a small helper that walks through nested keys and returns a fallback when something is missing. Now we run it on one complete profile and one profile without shipping data. Let's look at why this works. The helper checks each level before moving deeper, so missing shipping data becomes a normal fallback instead of a key error. This keeps optional JSON fields easy to handle. The best practice is to avoid chain direct indexing for optional nested JSON. Use get, a helper like this, or a validation layer depending on whether missing data is allowed. Payment JSON mixes strings, numbers, booleans, null, and values that look like domain objects. Let's parse the payload, print each Python type, then convert the date string explicitly. Now we run the script and inspect what Python actually created. Let's explain the important detail. JSON true becomes Python true, null becomes none, and the number becomes a float. But the date is still a plain string, so we use date from ISO format when the program needs a real date object. The best practice is to convert domain values at the boundary of your program. Do not let date strings, money strings, or special IDs drift deep into your code, pretending to be real domain objects. Now we move into JSON encoding and compatibility. These examples show how to keep international text readable and how to export Python values that JSON does not understand by default. Product data often contains names that customers should read directly, not as escape codes. Here we serialize the same catalog twice, first with ASCII escaping and then with readable UTF-8 text, and now we run the script to compare the output. Let's break down what changed. The escaped version is still valid JSON, but it is hard for humans to scan. The second version keeps the exact same values while making international names readable in logs, files, and reviews. The better choice for customer-facing files is to show readable Unicode. Use ensure OSCRI false when people need to inspect the JSON, and always write the file with UTF-8 encoding so the text is preserved correctly. Real reports often include datetime objects, but JSON only supports basic types like strings, numbers, lists, and dictionaries. First, we show the failure in a controlled way. Then we convert the datetime to a stable ISO string and run the script. Let's break down why this works. When JSON jumps finds a value it cannot handle, it calls our default function. The function returns a string, and strings are valid JSON values. The best approach is to choose the conversion yourself instead of relying on random string output, For dates and times, ISO 8601 is readable, sortable, and widely understood by APIs and databases. Next, we handle JSON that comes from outside the program. API responses should be checked in layers, status code first, parsing second, and field access after that. API clients usually give us a status code and a response body, and both need attention. In this example, we use a small mocked response. Check the status, parse the JSON body, validate the shape, and then run it to print the useful fields. Let's break down the flow. A 200 status only means the HTTP request worked. It does not prove the body is valid JSON after parsing. We still treat the data as external input and read fields carefully. The best production habit is to distrust the boundary. Check the status code, catch JSON parsing errors, and only then extract fields from the payload. Finally, we use JSON in workflows that look closer to production. We normalize messy input at the boundary and compare snapshots by meaning instead of fragile text formatting. Pipelines often receive user data from several sources, and each source names fields a little differently. Here we parse mixed records, normalize them into one internal shape, and run the script to print clean JSON lines for storage. Let's break down the benefit. The raw inputs disagree about ID, email name, and active flags. The normalize user function absorbs those differences once, so the rest of the pipeline works with predictable keys. The best place to normalize is at ingestion, right after parsing external JSON. That keeps source-specific cleanup out of business logic, tests, and database code. Snapshot tests often fail for the wrong reason, when JSON keys appear in a different order. Here we compare two response strings as raw text, then compare their parsed objects and finally print a stable sorted version for readable diffs. Let's break down the result. The strings are not equal because the characters appear in a different order, but once Python parses them, both objects describe the same status, count, and item. The best testing pattern is to compare parsed objects for correctness and only format JSON when you need a readable failure message. Sort keys true makes that displayed snapshot deterministic. Now we move into production-ready JSON workflows. This example shows how to process event data without loading a huge file into memory. Large event logs should not be loaded as one giant JSON array if we only need to process records one by one. Here we simulate a JSON lines file, loop through each line, parse it with JSON loads, and count the event types. Notice that the try block is inside the loop, so now we run the script and a bad line only creates a warning instead of stopping the whole job. Let's break down why this result is useful. Line 3 is broken JSON, so Python reports a warning for that specific line, then continues with the next record. The final counts prove that valid events after the bad line were still processed. The best practice here is to use JSON lines for high-volume event streams, logs, and exports. It keeps memory usage predictable because you handle one record at a time. In production, log the bad line number, skip or quarantine that record, and let the rest of the pipeline continue. Now you have a practical toolkit for working with JSON and Python without guessing. Like the video, subscribe to Dev Level Up, and write in the comments which Python topic or real-world example set you want next.